Welcome dear learners. We are continuing quantum chemistry and in this module we are discussing application of Huckel molecular orbital theory to conjugated systems. The contents of this module are HMO theory, Huckel's approximations, the secular determinant, application of HMO theory to 1,3-butadiene, benzene and cyclobutadiene. Finally, 4m+2 pi electron rule of aromaticity. So, first part of this discussion, HMO theory. In the just previous module, we learned about the basic aspects of Huckel molecular theory. The Huckel molecular orbital theory is a theoretical procedure that is used to solve the Schrodinger wave equation for conjugated pi electron systems more easily. This HMO theory is very easy to operate in the case of conjugated systems like simple organic molecules. Based on the Huckel molecular orbital theory, it is possible to predict the aromaticity of certain systems, etc. Now, we can just make a revision of the basic principles of, basic aspects of HMO theory first. HMO theory is primarily applied to conjugated systems where a series of alternating single and double bonds form continuous system of p orbitals. The theory predicts the distribution of pi electrons in a molecule by forming molecular orbitals. The Huckel approach, in this Huckel approach, the molecular orbitals are constructed from linear combination of p orbitals on carbon atoms involved in conjugated system. The ith Huckel molecular orbital psi I is given by this expression. Psi I is equal to sigma j is equal to 1 to n Cij phi j, where I is equal to 1 to 3 etc. up to n. That is, if we are having a system of n pi electron, there must have n Huckel molecular orbitals marked as psi 1, psi 2, psi 3 etc. up to psi n, and they can be represented as a linear combination of wave functions like this. Here, phi j is the 2pz orbital centered on carbon atom j, and in this expression, phi i's are known as the basis set. The overlapping of n pz orbital leads to the formation of n pi molecular orbitals. This is simply similar to molecular orbital theory, where atomic orbitals undergo combination to form molecular orbital. N atomic orbital combined to produce n molecular orbital. Similarly, n 2pz orbital on combination leads to the formation of n pi molecular orbitals in Huckel molecular orbital theory. Now, two kinds of integrals are highly relevant as far as HMO theory is concerned. The first integral is nothing but the overlap integral, and we know about overlap integral that this overlap integral is a quantity used to quantify the overlap of atomic or molecular orbitals, and by definition the overlap integral can be represented as Sij is equal to integral phi I star phi j d tau, or if phi I is a real function, then phi I is equal to phi I star. That is, if there is no imaginary part, the function should be same as its complex conjugate, that is phi I is equal to phi I star, and hence Sij, if you are considering real functions, Sij can be simply represented as integral phi I phi j d tau, and remembering the fact that this integral is a volume integral, whenever we are replacing d2 with dx into dy into dz, this integral must be shifted into volume integral, or simply we can represent Sij is equal to integral phi I phi j d tau, and this overlap integral is a quantity which represents the overlap of orbitals, namely phi I and phi j, centered on the atoms I and j. Now, the second integral that is of high applicability in HMO theory is the Hamiltonian integral. The name Hamiltonian integral is because of the fact that this integral consists of h hat. H hat is the popular Hamiltonian operator. that is the total energy operator. H hat is equal to minus s cross square by 2m del square plus v. It consists of a kinetic energy part and a potential energy part. H hat is termed as the Hamiltonian operator, and the integral contained H hat is termed as the Hamiltonian integral. And by definition, this Hamiltonian integral Hij is equal to integral phi I star H hat phi j d tau. And if we are having real functions, we can remove this star, no need for the star, because if we are discussing the real function, phi I should be same as phi I star. Therefore, I can simply remove this star, and Hij is equal to integral phi I H hat phi j d tau. And now, two important aspects of this Hamiltonian integral will appear in front of you when we are considering the value of I and j. If the value of I and j are not equal, that is, if I not equal to j, this Hamiltonian integral is termed as the exchange integral or resonance integral. Exchange integral represents the energy of interaction of the electrons in the atoms I and j. That is, exchange integral shows energy of interaction of the electrons present in carbon atoms I and j. Now, if I is equal to j, the second case, that is, if I is equal to j, then the Hamiltonian integral is termed as the Coulomb integral. That is, Coulomb integral is representing the two wave functions which are same. That is, Hij is taken as Hii. Hii is the Coulomb integral. Coulomb integral Hii is equal to integral phi I star H hat phi I d tau. Hii, both are I. So, phi I star H hat phi I d tau. So, I will make this point more clear like this. We have the Hamiltonian integral phi I H hat phi j d tau. If I is equal to j, we can mark it as Hii, and Hii equal to integral phi I H hat phi I d tau. This integral is termed as the Coulomb integral, and the Coulomb integral represents the energy of the electrons in the atomic orbital I centered on atom I. This is the situation. Now, Huckel's approximations on overlap integral and Hamiltonian integral. It should be noted that there are two kinds of integrals, namely the overlap integral and Hamiltonian integral, that is appeared in the Huckel molecular orbital theory. And based on some important approximations put forward by Huckel, it is very easy to solve the secular equation. Such approximations are called Huckel's approximations, and these are such approximations. Huckel made the following assumptions about three kinds of integrals. First two, Coulomb integral and exchange integral, are the Hamiltonian integrals, and also the overlap integral, to simplify the secular equation that we just mentioned. And the approximations are like this: Hij should be equal to alpha provided I is equal to j. That is, the value of all Coulomb integrals are same, and that is taken as alpha. Hij is equal to beta if I is equal to j plus or minus 1. That is, the value of exchange integral is Hij, Hij is equal to beta, and this is valid if and only if I is equal to j plus or minus 1. That is, there is only unit difference between I and j. And but if Hij is taken as 0 if I not equal to j plus or minus 1, and the next one Sij, overlap integral Sij is taken as 0 provided I not equal to j, and Sij is equal to 1 if I is equal to j. These are various Huckel's approximations that we are invariably useful in solving the secular determinant of systems as a part of HMO theory. Now, the secular determinant. In the Huckel theory for conjugated pi electron system, setting up of a secular determinant is of principal importance, and that is the first stage of the application of Huckel theory to conjugated pi electron systems. The HMO theory is similar to molecular orbital theory of homonuclear diatomics. In the HMO theory, the basis of functions are two pz atomic orbitals situated on carbon atoms of the molecule. For a system of n pi electron, a secular determinant of the order n by n should set first. That is the principal requirement of the Huckel molecular orbital theory. Now, the n by n secular determinant takes this long form. The first element of the determinant is h11 minus s11 e, then h12 minus s12 e, h13 minus s13 e, etc. up to h1n minus s1n e. Similarly, moving down, the last line is like this: hn1 minus sn1 e, hn2 minus sn2 e, etc. and final element in the determinant is snn minus snn e. And it should be noted that we have to give proper substitution of each of these elements based on Huckel's approximations. What are Huckel's approximations? The approximations are Hij is equal to alpha if I is equal to j, Hij equal to beta if I is equal to j plus or minus 1, Hij equal to 0 if I not equal to j plus or minus 1, Sij equal to 0 if I not equal to j, and Sij equal to 1 if I is equal to j. By putting all such approximations in this secular determinant in place of each and every element, we can simplify this secular determinant easily. The secular determinant needs to be solved based on Huckel's approximation. On applying Huckel's approximation, the above long form of the secular determinant takes the reduced form alpha minus e beta 0 0 etc. up to 0, beta alpha minus e beta 0 0, like that the RHS side will be equal to 0. And we can further simplify this secular determinant first of all by dividing each element present in this determinant by beta, and after dividing each element by beta, we can do another substitution, that is we have to substitute alpha minus e by beta as x. So, first of all I have to divide each and every component, each and every element by beta, and I have to put alpha minus e by beta as x. So, beta by beta is equal to 1 and alpha minus e by beta is taken as x. On applying that substitution where x is a dimensionless parameter, I can further simplify this secular determinant to a new form. This is the new form x1 0 0, 1x1 0 0, like that, and finally RHS will be equal to 0. So, the secular determinant, n by n secular determinant that we previously wrote now takes the simplified form this. On solving this equation further, we get energy and the wave functions corresponds to Huckel molecular orbitals of the system. Now, we can apply this Huckel molecular orbital theory to some conjugated systems, some conjugated organic molecules. Conjugated systems are those systems where alternate single and pi bonds are present. First of all, we are applying the Huckel molecular orbital theory to the system 1,3-butadiene. So, we are going to apply the Huckel theory, HMO theory to 1,3-butadiene. As we know, 1,3-butadiene molecule, 1,3-butadiene, this is the chemical structure of 1,3-butadiene. 1,3-butadiene can be considered as a conjugated system, alternate single and double bond, single bond, double bond. So, this is a conjugated system. So, this is a conjugated system with 2 pi bonds or having a total of 4 pi electrons. So, this 1,3-butadiene molecule is a 4 pi electron system, and hence, based on the Huckel theory, we have to write down a secular determinant of order 4 by 4 first, because number of pi electrons is equal to 4, n is equal to 4. So, the secular determinant needed to be solved is a 4 by 4 secular determinant, and we are now representing the 4 by 4 secular determinant and trying to solve that secular determinant. The secular determinant is of the form H11 minus ES11, H12 minus ES12, H13 minus ES13, H14 minus ES14, second row, H21 minus ES21, H22 minus ES22, H23 minus ES23, H24 minus ES24, third row, H31 minus ES31, H32 minus ES32, H33 minus ES33, S34 minus ES34. Last row, H41 minus ES41, H42 minus ES42, H43 minus ES43, and finally H44 minus ES44. And this determinant value is taken as 0. And we have to apply Huckel's approximations here. By putting different values for overlap and Hamiltonian integrals, we can solve this further, and as a further simplification, dividing each element by beta and to make the last substitution that we mentioned earlier, alpha minus e by beta is equal to 1, we can simplify it further, and in the form of x, this determinant is like this: x 1 0 0, 1 x 1 0, 0 1 x 1, 0 0 1 x equal to 0. This is the secular determinant, and this secular determinant can be solved to get the 4 values, and the 4 values are 4 Huckel molecular orbital wave functions, and that 4 Huckel molecular orbital wave functions corresponds to 4 different energy values, and then only we can arrange that 4 Huckel molecular orbitals in the increasing order of energy to get a molecular energy level diagram, and we can make further calculations. Thus, on solving the secular determinant of the above type, we are getting this expression x1 0 0 1 x 1 0 0 1 x 1 0 0 1 x equal to 0. And in order to solve this type of determinants, there will be an expression, and that expression is Ek is equal to alpha plus 2 beta cos k pi divided by n plus 1, where k is equal to 1, 2, 3, 4, etc. And 1, 2, 3, 4, because we are having only 4 atomic or 4 molecular orbital wave functions, and n is equal to 4 because we are having a total of 4 pi electrons, and we are discussing a 4 pi electron system. And this kind of matrix can be simplified by the expression Ek is equal to alpha plus 2 beta cos k pi divided by n plus 1. Thus, by putting different values for k, we get 4 expressions for energy levels, and that 4 energy levels can be like this: Ek is equal to alpha plus 2 beta cos k pi divided by n plus 1. This is the expression Ek is equal to alpha plus 2 beta cos k pi divided by n plus 1. If I am putting k is equal to 1, then I will get the energy level E1 is equal to alpha plus 2 beta cos pi divided by n is equal to 4, n pi by 5. n is equal to 4, so n plus 1 is equal to 5, because we are discussing a 4 pi electron system. And similarly, we are getting E2. If we are putting Ek k instead of k, if we put 2, then we get alpha plus 2 beta cos 2 pi divided by 5, 2 pi divided by 5. E3 is equal to alpha plus 2 beta cos 3 pi divided by 5, and last level E4 is equal to alpha plus 2 beta cos 4 pi divided by 5. And on substituting the value of cos theta, cos pi by 5, we can simplify this expression like this. E1, from this we are getting E1 equal to alpha plus 1.618 beta, and we are getting E2 equal to alpha plus 0.618 beta, and from this we are getting the expression E3 equal to alpha minus 0.618 beta, and finally from this we are getting the fourth energy level E4 is equal to alpha minus 1.618 beta. So we got 4 different energy levels, and these 4 different energy levels are energy levels corresponds to 4 Huckel molecular orbitals, namely psi1, psi2, psi3 and psi4. So we already mentioned the fact that alpha and beta are negative quantities. So psi1 is the lowest energy level, and to get to the lowest energy level, the energy level E1 must be alpha plus 1.618 beta. So on solving the secular equation, we are getting 4 different energy levels, and these 4 energy levels corresponds to 4 Huckel molecular orbital, psi1, psi2, psi3 and psi4. Thus these are the 4 energy levels. The first 2 energy levels are considered as psi1 and psi2 are considered as, or E1 and E2 are the energy corresponds to molecular orbital psi1 and psi2. Psi1 and psi2 can be considered as the bonding molecular orbital, and the last 2 energy levels E3 and E4 corresponds to molecular orbital psi3 and psi4 can be considered as anti-bonding molecular orbital. And we can plot the energy level diagram of 1,3-butadiene like this. This is the energy level diagram of 1,3-butadiene. Energy is in the increasing order. The lowest energy is for psi1, and psi1 is having an energy equal to alpha plus 1.618 beta. The next level is nothing but psi2. It is associated with an energy alpha plus 0.618 beta. Then another energy level is psi3. Psi3 is having an energy of alpha minus 0.618 beta. And the next level is psi4. Psi4 is the 4th Huckel molecular orbital. This is a separation. This is an energy separation. And this psi4 corresponds to an energy alpha minus 1.618 beta. And these 2 first levels are considered as bonding molecular orbitals, and the last 2 are considered as anti-bonding molecular orbitals. We can put pi electrons here. 2 pi electrons are present here. The 1,3-butadiene is a 4 pi electron system. 2 pi electrons are present in the energy level E1 or molecular orbital psi1, and other 2 electrons are present in molecular orbital psi2. So this psi2 can be considered as highest occupied molecular orbital, and psi3 can be considered as the lowest unoccupied molecular orbital. This is about the energy level diagram of HMO energy level diagram of 1,3-butadiene. Now we can make some calculations based on the previously mentioned energy level diagram, and in the previously mentioned energy level diagram, the total pi electrons energy, is obtained by multiplying number of pi electrons with the energy of the level in which the pi electron is present. So 2 pi electrons are present in psi1 with energy alpha plus 1.618 beta. Other 2 pi electrons are present in the energy state with energy alpha plus 0.618 beta. So on simplification, we are getting total pi electrons energy, the energy of the 4 pi electrons present in 1,3-butadiene as 4 alpha plus 4.472 beta. Now we are going to evaluate a very important parameter based on the Huckel molecular orbital theory, and that parameter is called delocalization energy or resonance energy. The delocalization energy of the present system can be calculated by using the expression dE equal to total pi electrons energy minus energy of ethylenic pi bond. What is meant by the term energy of ethylenic pi bond? Previously we learned that ethylene molecule consists of a pi bond with energy 2 alpha plus 2 beta. This is the energy of the pi bond in ethylene. Energy of the pi bond in ethylene is called the energy of ethylenic pi bond. Energy of ethylenic pi bond is a constant value, that is 2 alpha plus 2 beta. But in ordinary butadiene is a system which consists of 2 pi bonds. Therefore, in ordinary butadiene there are two ethylenic pi bonds. Therefore, to get to the delocalization energy of ordinary butadiene, we have to use this expression. Delocalization energy is equal to total pi electrons energy minus energy of ethylenic pi bond. Total pi electrons energy is, we proved it as 4 alpha plus 4.472 beta minus energy of 2 ethylenic pi bonds, because 2 ethylenic pi bonds are present in ordinary butadiene. 2 ethylenic pi bonds has a total energy 2 into 2 alpha plus 2 beta, that is 4 alpha plus 4 beta. Hence, on substitution or subtraction of this quantity from this, we are getting the delocalization energy of ordinary butadiene as 0.472 beta. So, delocalization energy or resonance energy is a stabilization parameter. Based on that, we can assess aromatic stabilization in cyclic conjugated systems like benzene. In this ordinary butadiene, the resonance energy or delocalization energy is 0.472 beta. That means ordinary butadiene is more stable compared to 2 ethylene molecules by a factor 0.472 beta. This means whenever we are coupling 2 ethylene molecules to get ordinary butadiene, if we imagine like that, ordinary butadiene will be more stable if we are considering the stability of 2 ethylene molecules. That is, ordinary butadiene is more stable compared to 2 ethylene molecule, and the stabilization parameter is reflected as delocalization energy. Its value is 0.472 beta. Now, the molecular orbital wave functions. Similarly, in situation similar to that we applied in the case of ethylene molecule, it is possible to find out the coefficients of linear combination to get the complete molecular or Huckel molecular orbital wave function. We know there are 4 HMOs associated with ordinary butadiene. They are psi1, psi2, psi3 and psi4. After evaluating the coefficients, we are getting the complete expression for 4 Huckel molecular orbital wave functions. These are 4 Huckel molecular orbital wave functions of ordinary butadiene. Now, we can take another example, that is a cyclic system, and that system is benzene. So, we are now studying application of Huckel molecular orbital theory to benzene. We know benzene can be considered as a cyclic conjugated system with the 6 pi electrons. Notably, it should be clear that n is equal to 6. So, we have to solve a 6 by 6 secular determinant, and the 6 by 6 secular determinant should be of the form. After simplifying by putting with x etc., we need not to start from the very beginning. In the very beginning, we are representing the complete secular determinant, 6 by 6 secular determinant. Then we have to make substitutions based on Huckel theory. Then divide each element with the beta. Then we have to give another substitution, alpha minus e by beta is equal to x. After that, we are getting an expression like this. For 6 pi electron system, we are getting this expression x 1 0 0 0 0, 1 x 1 0 0 0, 0 1 x 1 0 0, 0 0 1 x 1 0, 0 0 0 1 x 1, and finally 0 0 0 0 1 x. This must be equal to 0. This is the general form of 6 by 6 secular determinant. But a very important thing we have to consider here is that we previously learned some systems like ethylene, non-butadiene, etc., but they are not cyclic systems. But we are now considering the benzene molecule. The benzene molecule is a cyclic conjugated system. In representing the secular determinant of cyclic conjugated systems, we have to make a slight correction in this secular determinant. This is actually the secular determinant for 6pi electron system like 135 hexatriene. But we have to discuss the secular determinant of cyclic conjugated molecule benzene. So, this is the secular determinant for a 6pi electron system which is open, which is not a cyclic molecule. So, this is the secular determinant for 135 hexatriene. So, when it is changed to cyclic systems like benzene, we have to make a small correction in this secular determinant. The correction is like this. Instead of this 0, I have to put 1, and instead of this 0, I have to put 1. That is, last element of the opposite diagonals must not be 0, it must be 1. For cyclic system, the last elements of the opposite diagonal, this is principal diagonal which is always x, this is opposite diagonal, terminal elements of the opposite diagonal must be 1. Hence, for benzene molecule, the determinant is like this, x1 0 0, the last element is 1 and this is 1. And these are zeros in the case of cyclic systems, and these are 1 in the case of cyclic systems like benzene, cyclobutadiene, etc. And now we have to solve this secular determinant. This secular determinant can be simply solved by using a generalized expression. Ek is equal to alpha plus 2 beta cos 2 pi r divided by n, where r is equal to 1, 2, 3, 4 and 5 and n is equal to 6. By putting various values in this position of r and n is equal to 6, we will get 6 different values for energy levels, out of which some levels may be same. If 2 levels have same energy, it is said to be doubly degenerate, and we got this energy levels for benzene. E1, that is a low energy system having an energy of alpha plus 2 beta. We previously studied that alpha and beta both are negative quantities. So, E1 is the low energy state and its energy is alpha plus 2 beta, that is a bonding molecular orbital. E2 and E3 have the same energy alpha plus beta, so it is said to be doubly degenerate. They are also bonding molecular orbital. E4 and E3 have energy alpha minus beta, and E6 have an energy alpha minus 2 beta. So, these are various energy levels, and it is possible to plot these energy levels like this. 2 electrons are in BMO and other 2 electrons are present in Psi2 and Psi3 BMO. This is about the energy level arrangement of benzene molecule, and we can do some calculations. As we mentioned in the case of 1-butadiene, here also we can find out the total pi electrons energy of the total pi electrons, that is theoretically equal to or calculated to be equal to 6 alpha plus 8 beta. And the most important parameter, delocalization ratio of resonance energy, which is again calculated by using the expression total pi electrons energy minus energy of ethylene pi bond. Here in benzene 3 ethylene pi bonds are there, therefore the total energy of ethylene pi bond is equal to 6 alpha plus 6 beta. One simple calculation, the delocalization energy of benzene is got as 2 beta. Hence, it should be noted that benzene is a molecule which is highly stabilized by resonance. Now, these are 6 HMO wave functions for benzene, and this is based on linear combination principles and principle of secular determinant. We are evaluating the coefficients of linear combination, and the wave functions of benzene are like this. Now, we are applying this HMO theory to cyclobutadiene, which is another cyclic system. This molecule is called the cyclobutadiene. Here we can see the presence of 2 pi bonds and 4 pi electrons. Hence, we have to solve a 4x4 secular determinant. Since it is a cyclic system, the secular determinant is like this. Here also the opposite elements are 1 terminal elements of the opposite diagonals are 1, and by applying the same principle we can solve this expression, and on solving this we are getting 4 energy values for cyclobutadiene, and these are the 4 energy values. One level is doubly degenerate, and this is the energy level diagram, and psi 1 is the lowest energy level with minimum energy alpha plus 2 beta, 2 electrons are present there. Other 2 electrons are present in psi 2 and psi 3. This is about the electronic arrangement, and based on this electronic arrangement, it is possible to do some calculations, and the total pi electrons energy of the system is equal to 4 alpha plus 4 beta, and we are now going to evaluate the delocalization energy or resonance energy of the system, and that is calculated to be equal to 4 alpha plus 4 beta minus 2 ethylene pi bonds are there. So, we have to deduct 4 alpha plus 4 beta, and the final value of the delocalization energy equal to 0. Hence, it implies that the molecule cyclobutadiene is not stabilized by resonance. This is because there is no resonance stabilization, and delocalization energy is 0. But in benzene, we proved that the delocalization energy is equal to 2 beta. Hence, based on Huckel theory, it is possible to evaluate the delocalization energies of several cyclic conjugated systems. And based on this, Huckel put forward a very important rule. That rule is called Huckel's 4m plus 2 pi electron rule of aromaticity. And this Huckel's 4m plus 2 pi electron rule of aromaticity is based on resonance energy calculations of cyclic conjugated systems as per HMO theory, and this 4m plus 2 pi electron rule of aromaticity states that for a cyclic planar system with a complete delocalization of 4m plus 2 pi electron, n is equal to 0, 1, 2, 3, etc., will exhibit aromaticity. Any cyclic planar system with a complete delocalization of 4n plus 2 pi electron will be more stable, that is, they will exhibit aromaticity. This is Huckel's 4m plus 2 pi electron rule of aromaticity. That all about the present module. Have a nice learning experience. Thank you.